So today we are going to talk about equations, chemical equations. So what's a chemical reaction? Our chemical reaction involves our chemical change of our matter. And we already talked about some chemical changes. So a chemist has ways to represent chemical changes, and that's by our reaction equations. So you might hear this as chemical equation or chemical reaction. And this is when we have changes that somehow result in a new substance. Those reactions might involve a rearrangement, it might involve an exchange of atoms, we might produce new molecules, and we'll talk about more of those things throughout the class. The way chemical reactions are written are reactants, and then an arrow, and then products. Sometimes this arrow is going one way. That represents a reaction that's what we consider pretty much irreversible. But we might have an arrow going one way and then an arrow going back to reactants. And that usually represents a reaction that's highly reversible. All reactions in theory can be reversed, but sometimes it just takes too much energy, so it's really unlikely to happen. And we'll talk more about energy in Chapter 6 and those kinds of concepts and mapping out that energy. So on our left side, we always have our reactants. That might be two, like in this case. There might be multiple reactants. It depends. And then our products are on the right. Oftentimes, we'll show all products, but sometimes in organic chemistry, we just might focus on the organic molecule. So you have to look deeper to know what the full chemical reaction is. The way we write our reactions are symbolic for meaning certain things. So there's a couple of symbols that you're going to need to know. And it's so that a chemist anywhere, no matter what language they speak primarily, can read and understand our chemical reactions. So these different symbols mean certain things. So our chemical equation is a shorthand way of describing our reactions, and we provide a lot of information about the reactions. So of course we have our formulas of reactants and products. That's pretty clear. We know how many atoms total are reacting in the molecule. We know a lot about that. The other thing a full chemical equation will show is our state of our chemical matter. For example, what we see here is CH4 and we see a G. That represents that our methane is in the form of a gas in this chemical reaction. We also show relative numbers of reactant and product molecules that are required to react with each other, especially in a full chemical reaction in a 1-to-1 ratio. So we're going to talk about that and talk about balancing our equations and why that's important. Our chemical equation tells us a lot of things. We can use that to determine the weights of reactants used. We can predict how much products we expect to form. So if I'm in a chemical lab and I want to make something, I want to make a compound, I want to do a reaction, I want to make a certain compound. And I want to make 5 grams of the compound. Well, I need to know how much starting material I start with. So kind of like if you are cooking and you want to make 12 deviled eggs. How many eggs are you going to boil? 6, assuming that you don't have any loss. So that's what our chemical reaction can help us do. It can tell us what we need to start with. If we know how much of something we're starting with, we can predict how much possible product we can form. So it tells us a lot of our chemical equation. So let's look at the combustion of methane. We're starting with combustion again. We've kind of looked at combustion. Methane gas, what our reaction tells us is methane gas will react with oxygen that's also in the gas form to form CO2 that is in the gas form and water in the gas form. So that tells us all that from our chemical reaction. And this is our little representation. This isn't our full chemical reaction. Something's missing. One thing that's missing is, notice we started with 4 hydrogens and we only end up with 2. So we're missing something. Those other hydrogens had to go somewhere. But the big thing is we started with 2 oxygens, and in our final product we have 3. That can't be. We can't start with 2 and end up with 3. Where'd that third oxygen come from? So we have to have more in our chemical equation. We have to have it balanced to where we are following our law of conservation of matter.
Friday.
It's true. That's okay. Technical difficulties. So we have to have more to this. So there is more in our chemical equation that we need. Because this can't be correct, we can't form 3 oxygen atoms if we're only starting with 2. So more must be needed. So that's going to be balancing our equation, and it's why it's important. So the incorrect assumption is that we only need 1 CH4 molecule to react with 1 O2 molecule, and that's not true. We need multiple of these molecules for a full reaction to occur. So that the way we show that and balance our equations to agree with the law of conservation of mass is by these coefficients that go before our molecules. And we're going to look at balancing equations in a lot of detail. Now, some reactions will be a one-to-one reaction, but we need to be able to determine if that's true. So to show that, we use a balanced equation and we use these numbers. Now, again, just like in most of chemistry, if the number is 1, we don't show it. It's not necessary to show a 1, just like we don't show a 1 after our carbon, even though we know we only have 1 carbon for each CH4 molecule. So we're not showing 1s. That's pretty normal. So we got to adjust our numbers of molecules. So our total numbers of each atom that we start with is how much of our total numbers of each atom that we end up in the end. Sometimes this is easy to see, sometimes it takes a little bit more, so we'll be going through this. So if we balance this, we see that if we actually start out with 2 molecules of O2, we're going to form 2 molecules of water, but now we're balanced. We have only 1 molecule of carbon on each side of our arrow. We started with 4 molecules of hydrogen, and we still have atoms. We still have total 4 atoms of hydrogen, though of course it's in a different form. And then we started with 4 atoms of oxygen, and in our final product we have 4 atoms of oxygen. Now this is typically we show our stoichiometry and our lowest whole number ratio. Technically, we could have started with 4 molecules of CH4, but then we need 8 molecules of O2. So typically we just start with our lowest whole number ratio. Because clearly, in an actual chemical setting, we're not going to have 1 molecule of CH4. That's very hard to do. It's a very, very small compound. So we usually have a sample of multiple of these. So we just use our lowest whole number ratio. And we can always double check to make sure we have the same amount of atoms on each side of our arrow, because the law of conservation of mass, you can't make something from nothing. And my analogy I like to use is, again, if you're baking cookies and you want pecans in your cookies, you have to add them. And if you didn't have pecans in your cookies and you have them after they baked, you need to get out the house because someone's probably in there. And you really want to watch out for that. And I don't know why someone would break in your house and add pecans to your cookies, but if you're allergic to pecans, they might be trying to kill you, so you might want to leave. So we can't make something from nothing, which is why it's important that we balance our equations. So we're going to talk about balancing equations. So reading our chemical equation, this chemical equation tells us that we have CH4 and O2 are reactants, and we need 2 moles of O2 for every 1 mole of CH4 for a full reaction to occur. If we only have 1 mole of O2, we will not get a full reaction to occur. So we don't have enough. And then our products are CO2 and H2O. And for every reaction, we're going to get 2 moles of water, but only 1 mole of CO2. That's what it's telling us. Now, these things tell us our state. The G means gas, and our states of reactions are pretty easy to know, our symbols. And then the numbers in front are our coefficients. Now, we can change the number of coefficients, but we cannot change the number of hydrogens bonded to carbon because that would be a different molecule. So when we're balancing our equations, we can change our coefficients, but we can't change what our actual molecules look like. That's very important. So to balance our equation, we must have equal numbers of atoms on both sides. So we can look at our coefficients and double check that. Like I said, our symbols are pretty easy. We already talked about AQ. That means dissolved in water. We talked about that's important for acids. So when you see AQ, that means it's dissolved in water. And when we talk about solution reactions in the next couple of chapters, we're going to have that. It's going to be really important. Gas, of course, is a G. L is liquid, and S is solid. So pretty straightforward with most of those symbols. And as we come into new symbols, we'll talk about them. Energy symbols might be used above the arrow to represent things like decomposition. So the energy symbols that you need to know, a triangle or delta. It's really delta. It's a capital delta in the Greek language. It means heat, and it'll also mean change later on when we talk about energy. So we'll use delta in 2 things. H nu, it looks like HV, but it's actually a nu. That means light, so light's applied to the reaction to make it occur. You might see, but not as much in this class, shock and elect. That means a mechanical, so we had to mechanically agitate the reaction to make it occur. Or electrical, that's usually really important for oxidation reduction reactions, might have to occur for the reaction to occur. Well, we'll see a lot more is heat and light. We use heat a lot for reactions, so you need to know those symbols. Sometimes those are above the arrows. Sometimes above the arrow we might have a catalyst, or we might have a catalyst below the arrow, and as we get to examples like that, I'll point them out. So there's a couple of things that we'll learn as we go on. But these you need to know. They're pretty straightforward, though. So let's do some balancing of equations. So remember, the key for this balancing of equation is that we have to have the same amount of atoms of each element that we start with and that we finish with. And it's all based on our law of conservation of mass. So you can follow these. You don't really have to, but these are just to help you. So our first thing, if we don't have the actual skeletal equation, we have to write it. Now in this case, we're told that we are undergoing the combustion of butane, and we know combustion is reacting our carbon-containing compound with O2 to form CO2 and H2O. That's always going to be combustion. Now later on, we're going to talk about combustion in more detail and what reactants form, what products form when we start with a reactant that have sulfur and things like that. Right now, you don't need to know that. Right now, you're just going to be forming CO2 and H2O if you get a question like that. So our first step is writing our actual skeletal structure. We need to know what the equation looks like before we can balance it. So we are reacting C4H10 and in this case I might have to tell you that C4H10 is liquid at room temperature. You probably wouldn't know that offhand. I know that. You should kind of know that because everyone in here has probably used a butane lighter and it is a liquid. But if it's something like that, I would have to tell you because you're not really at that point to be able to predict when a carbon-containing molecule is going to be a liquid or a gas. But it's a liquid, so I'm going to put the L. Plus O2, because that's combustion. That's a gas. Forms CO2 gas plus H2O. Okay, so that's my skeletal but it's not balanced. So next we need to balance our atoms. The way I'm going to show you how to do this is not necessary that this is how you have to do it, but the way I'm going to show you how to do this I find helps me when I'm teaching and helps students that have problems with this. Some of you in here might be really good at balancing equations already, and that's great, but some of you might not have really ever had to do this or did it 10 years ago or whatever. So I'm going to show you a way that I find helps when I teach, and that's by making a chart. But you do not necessarily have to make the chart, but I will say it helps you keep track of what you're doing. So that's what I'm going to do for these two examples I'm going to go through. So I'm going to make a chart where I have a reactant side and my product side. And on both sides, I'm going to write my atoms. So I have carbon, hydrogen, and oxygen on my reactant side, and of course my product side I have carbon, hydrogen, and oxygen. So that's true for this reaction. So now I'm going to write the number of each of the atoms I have starting off. What I have written down in my skeletal. So with my skeletal I see I have 4 carbons, 10 hydrogens, and 2 oxygens. And then for my final product, I see I have 1 carbon, as it's drawn now, 2 hydrogens, and total how many oxygens? This is a common problem. We have 3 total oxygens. They're in 2 different molecules, but we do have 3 total oxygens. So that's how I like to start. Now again, you don't necessarily have to do this, but I find it helps. Now I'm going to keep track of any change I do to my reaction here on both sides, and I'm going to be done when it's equal. So you can kind of play around with what you should start with. The easiest thing for this example to start with is working with hydrogen or carbon, because in the product I have oxygen in 2 separate molecules, so that's going to be a little bit more difficult to work with to start. So carbon is only in 1 molecule in my starting material and 1 molecule in my final product, so it's a bit easier to start with. So I'm going to start with trying to balance carbon. Now I might have to change this throughout this process, but that's where I'm going to start. So I'm going to say I only have 4 carbons that I started with, but I only have 1 in my product, so let's put a 4 here. So here in my little thing, I'm going to put 4 CO2. And now I'm going to track how that changed. And I still have 4 carbons to begin with, 10 hydrogens, and 2 oxygens because I didn't do anything to my starting material. But now I have 4 carbons. I still have only 2 hydrogens because I didn't do anything to the H2O term. But now 4 times 2 is going to be 8. And adding that to my other oxygen, that's 9. Everyone sees why that's 9? Okay, so now I'm just going to, okay, my carbons are balanced. That doesn't necessarily mean I'm done with my carbons, but that's an easy thing to start with. And the next easiest thing to do is balance my hydrogens, because again, I only have hydrogens in 1 molecule in my starting material and 1 in my final product. So that's a nice, easy step to go to next. So I have 10 hydrogens in my reactants, but I only have 2 in my products. So if I multiply my H2O term by 5, then I can get somewhere. This thing isn't real calibrated once I get to the right side. Okay, so just going to put 5 H2O here. So now I still have 4. I haven't done anything with my reactants yet, so that's still the same. Now I have 4 carbons because I didn't change anything there. And now I have 10 hydrogens. But now total, again, I have 8 oxygens here. And here I have 5, because 5 times 1. So total now I have 13. 13 is a little tough, because there's no number I can multiply oxygen by that's going to give me 13. But when you come to an odd number like this, what you can do, oxygen, what if I multiplied my oxygen term by 13 divided by 2? Then I'm going to have a balanced equation. Now I know you're going to say, Dr. Cortez, I thought we went with the lowest number whole ratio. That's okay, we'll get there. So now everything else is balanced, it's cool, we're good. But my oxygens aren't balanced. So what I can do when I come, if this was 14, that would be great. I can multiply O2 by 7, I'd be all great. But it's not. So what I can do is, let's say I'm going to put 13 divided by 2 in front of my O2. So now, again, I haven't changed anything with my carbons in my starting material, my hydrogens. But now I have 13 oxygens. 13 divided by 2 times 2 is 13. And I didn't change anything more with my products. So now I'm balanced, but I don't have the lowest whole number ratio. But that's okay, because I can fix that, because I can multiply my whole chemical equation by 2. And that'll give me my lowest whole number ratio. But you have to, the key here is you have to multiply the whole chemical equation, reactants and products. So if I multiply the whole thing by 2, my 2 will cancel out, and I will have two times C4H10 plus 13 O2 produces 8 CO2. Remember, nothing changes with my molecule. I always have 2 oxygen atoms for 1 carbon, plus 10 H2O. There is no number I can divide every coefficient by to get a lower whole number ratio. Now my last step is I want to check. If I did this correctly, and I follow exactly what my equation says, I should have a completely balanced reaction. So my check for my final, I'm going to have 8 carbons in my starting material, 2 times 4, 20 hydrogens, and then 26 oxygens. And my final product, I have 8 carbons, I have 20 hydrogens, and then I have 16 oxygens in CO2 and 10 in my H2O term. So that is a total 26. My oxygens are balanced, my hydrogens are balanced, my carbon is balanced, and there is no number I can divide all of these by. So this is my balanced equation. Again, you don't necessarily have to set up this chart, but I find it really helps you from making a mistake. Now, you won't always have to use this, but when you get an odd number like this, it's really helpful. What I say about balancing equations is kind of like solving a puzzle. And I can't sit here and tell you, if I gave you a jigsaw puzzle, I can't really sit here and tell you how to solve that puzzle. Some people like to do the outside first. Some people like to do the middle and then do the outside. Some people like to do a part here, a part there, and then put it together. This is solving a puzzle. You have to find the best way for you to solve this puzzle. I'm just going to try to teach it in a systematic method that you can go and follow if you need. But you really have to find your way to solve this puzzle. And the only way you can do that is by working problems and working problems and working problems. Always check your work with these. It's very easy to check because you know your atoms have to be balanced on both sides. So you can always check your work with these kinds of questions. Let's go through another example. Okay, so here, this is saying aluminum is reacting with air, produces a white powdery compound, aluminum oxide. Air has a lot of things in it, but aluminum oxide, you know what that has in it. You know how to draw aluminum oxide. So you should be able to draw that final product. So our first step is going to be to write our equation. Reacting with air means it's likely reacting with O2. I know that because all I have in my final product is aluminum and oxygen, and air has O2 in it, so it's likely that. So that's likely going to be O2. So that's one background information that you kind of need to know for this one. So our aluminum is a metal. Remember, metals are solid when it's in its elemental state. It's going to react with O2 gas. Remember, that's a molecular element. And you need to know these molecular elements, because if I tell you something reacts with oxygen, you need to know that's O2. If I tell you something reacts with chlorine gas, you need to know that's Cl2. So you do need to know those molecular elements that we talked about in chapter 3, and chapter 3. This is still chapter 3, but earlier in the chapter. So we talked about those. And that's going to form aluminum oxide. So you need to know how to convert that name to a structure, which we talked about as well in this chapter. So aluminum and oxygen can combine to form Al2O3. Now aluminum, remember, is in the periodic table. It's in group 3. So we form that +3 ion. Now if it was a variant charge, you'd know that because you'd have in parentheses the charge. So you still need to know how to convert the name to the structure. So this is our chemical equation, but it's not balanced. So now we need to balance our chemical equation. Well, we don't know if it's balanced. We'll know when we do our start. And when we do our start, if it's balanced already, we don't need to go further. So again, I'm going to set this up just like I did before with a chart, just because I find it's the easiest way to teach this to a large class and the most effective. Because honestly, it's really hard to teach things that you're really good at, and I can balance equations really easily. I've never had a problem with it. So I find that this route helps everyone the best. Everyone's good at some things better than others. I'm really good at math. But that means sometimes it's hard for me to explain it to other people, because I just do it. So let's go again. I'm going to put my reactants and my products. I'm just going to put R and P just to do that. And of course, in my reactants, I only have, in this case, aluminum and oxygen. And in my products, I only have aluminum and oxygen. So this one's a little bit easier than the example we did before. So at my start, I always want to start and kind of get an idea of what I have. If you're baking, you're probably going to go to the pantry and see how many eggs you have before you start deciding how much you're going to bake. So we want to know what we start with. So we have in our equation, we have 1 aluminum atom, and we have 2 oxygens in our reactants. That produces in our products 2 aluminums and 3 oxygens. So we're not balanced. Our aluminums aren't balanced, our oxygens aren't balanced, so we have to go further. This one's pretty straightforward because we are taking 2 things and making 1 thing. So this one's a little bit easier to balance and see probably. So you might not need this chart as much, but just to be clear and to be safe, we're going to keep with the chart. So let's start with oxygen. We have 3 oxygens in our final product. And we have only 2 in our starting material. So if I multiply my starting oxygen with 3 and my final product with 2, I'll be able to balance it. So let's start with 3, because there's no outward easy route to balance our oxygen. Now I could start with aluminum and balancing it with a 2, but I'm going to have to change it eventually. And you'll see that if you're playing around with it. So let's start with 3O2. So we'll put a 3 there. So my aluminum, we still just have 1. We didn't do anything. We have 6 oxygens. And in our products, we still have 2 and 3. But I'm getting closer because I have 6 oxygens in my starting material and I have 3 in my final product. I can multiply my product by a number to get 6 because 3 is a portion of 6. It's pretty straightforward. So what I can do is I can then multiply my product by 2, because 2 times 3 is going to give me 6. Again, I didn't do anything with the aluminum that I started with. I still have 6 oxygens in my starting material. But now, I have 4 aluminum atoms in my product, and I have 6 aluminum atoms in my product. So my oxygens are balanced, but my aluminums are not yet. The nice thing is, aluminum solid by itself has no multipliers. I have 4 in my product. I only have 1 in my starting material, so that's a pretty easy fix. I can multiply my aluminum by 4. So now I have 4 aluminum atoms in my starting material. Didn't do anything with my oxygens. I still have 4 aluminum atoms in my final product. And I have 6 oxygens. So now my oxygens are balanced. My aluminums are balanced. And I just want to go ahead and double check that there's no whole number I can divide this by to get any lower ratio. I can divide by 1, but that won't change anything. So this is my lowest whole number ratio, so this is in fact balanced, and my check is in agreement. Again, the more you practice, the better you'll get at seeing these and solving this puzzle. But your main thing is you are balancing both sides of the chemical equation. Let's do one more. This one has a bit more molecules in it. And there's also something else with the way this is drawn that I want to point out when balancing. So the reason why this particular compound is drawn where our hydrogen is separate from our other hydrogens is because acetic acid is an acid, and that hydrogen is being transferred to form H2, and we're forming our acetate ion, C2H3O2. So that's just more clearly showing it. Sometimes our chemical formulas don't show our connectivity very well, so we can do that. But that means total in that molecule, HC2H3O2, we actually have 4 hydrogen atoms. It's just drawn to represent that that hydrogen is the one that's being removed to form an ion. And in organic chemistry, we wouldn't draw it in this formula like this. It would be easier to balance the equation if it was drawn in skeletal structure. So we talked about some of those molecular representations earlier at the end of chapter 2. And that would be one of the cases where we show connectivity very well. So the reason why this one's broken up like this is to show the connectivity and to be more clear about what's happening in the reaction. That we're losing this H and forming a C2H3O2 ion that is going to form an ionic bond with aluminum. Do I expect you to figure out these products at this point? No, I don't. I don't expect you. If I gave you aluminum solid and I told you it reacted with acetic acid, I wouldn't expect you to come up with this product on your own at this point. You will work towards this in this class, but I just wanted to point that out. But don't get lost just because the 2 hydrogens aren't 4 shown here but broken up. That still doesn't change the total amount of hydrogens you have in your starting material side. So we're going to figure this out. Now if I told you it formed aluminum acetate, of course you should be able to draw that product because you should be able to take your ionic molecule, your ionic compound, aluminum acetate, and draw what it looks like. So you should be able to do that because we talked about that in chapters 3. And also you should know that when hydrogen is in the gaseous or elemental state, it's in H2. So that's another one of those diatomic molecules, a molecular element. So now that we have our equation, then we can balance it. So again, I'm going to make my nice little chart because I think it's the easiest way to explain what we're doing. Oh, my chart's in red this time. And I just put reactant and product so I don't get lost when I'm doing these. Okay, so in our reactant sides we have aluminum. we have hydrogen, we have carbon, and we have oxygen. It looks like we have more, but we don't. And our product side, we have aluminum, hydrogen, carbon, and oxygen. And I'm just, to be consistent for myself when I'm doing these, I just keep them in the same order, just to be consistent. That's really the only reason why I'm doing it, so I don't get lost when I'm doing this balancing. So the first thing I like to do is, what am I starting with? So I am starting with 1 aluminum atom, and I am starting with 4 total hydrogens. That's important that we recognize that. I have 2 carbons, and I have 2 oxygens. In my product side, I have 1 aluminum. Here's another reason why I wanted to do this example. I'm not going to calculate my hydrogens just yet. I have 3 C2H3O2 ions in this ionic compound. That's what that parentheses means. So that means for this compound, the way it's drawn, I have 3 times 2 carbons. That's 6 carbons. I have 3 times 3 hydrogens. That's 9 hydrogens. And I have 3 times 2 oxygens. That's 6. So I'm not starting with 2 carbons. I'm starting with 6 carbons, 6 oxygens, and 11 hydrogens. Because I have 9 here, and I have 2 here. Your first step is to basically take note of what you have. Before you go shopping, you count how much money you have in your wallet, hopefully, or your bank account, hopefully. You should really look at that before you go shopping. So we want to count and see what we have before we start trying to change anything about our balance, our stoichiometry. This will help. So remember, that means we have 3 C2H3O2 ions. So we have to take that into account. Okay, so that's our first step. We know what we're starting with. We're clear that we're not balanced because, well, we don't have the same amount of carbons, oxygens, or hydrogens on both sides of our equation. We have the same amount of aluminums. Aluminums by itself, it's easiest to finish with because if I change the coefficient in front of aluminum, it doesn't change anything. So let's save that one for last if we need to balance aluminum. So we'll save aluminum for last just because it's really easy to balance aluminum. It's by itself. So let's start with, and again here, this is one of those cases where the more you practice, the more you'll get good at what you're going to start with. So what I am going to start with is, I have less carbons in my starting material than my final product. And I only have carbons in 1 molecule in my starting material, 1 molecule in my product. And the same thing with oxygen. I only have it in 1 molecule in my starting material, 1 molecule in my product. So they're a little bit easier to balance. So I have 2, and then I have 6. If I multiply this whole thing by 3, I'll have 6. And I'll also have 6 oxygen. So that's a good place to start. Because again, hydrogen is in 2 different places in my product. So that one's going to be a little bit harder to work with. So let's start with multiplying this by 3. I'm going to call that, just for ease in me writing it, I'm going to multiply that 3 by my species that I'm calling 2. Just so I don't have to rewrite HC2H3O2. So once I do that, that doesn't change anything about the amount of aluminums I have in my starting material. It doesn't change anything about what's going on in my final product. So I'm just going to rewrite that. Well, what it does change is the amount of hydrogens, carbons, and oxygens I have in my starting material. So first, let's start with carbon. That's pretty easy. 3 times 2, that's 6. Oxygen, 3 times 2, that's 6. Hydrogen, 3 times 1, we have 3. And then 3 times 3 is 9. So that gives me 12. Oh, we're so close, but we're not quite there. Our carbons are balanced, our oxygens are balanced, our hydrogens are not balanced. So where should we go from here? Well, the easiest thing to do now is going to be to work with H2. Because if I do a multiplier in front of aluminum, it's going to change everything with my carbons and my oxygens, and I got to go back to this and do all kinds of things. But H2 is by itself. So let's think about changing that. So remember, I have 9 hydrogens in, let's call this species 3, just for discussion, and let's call this molecule 4. So I have 9 hydrogens in species 3, and I'm adding that with my 2 in species 4, right? So that gives me 11 total. If I had 3 total hydrogens in species 4, that would be 9, 10, 11, 12, right? Now, is there a whole number I can multiply H2 by to give me 3 hydrogens? Not a whole number, no. But I can multiply it by 3 over 2. So let's try that. If I multiply this by 3, sorry, it's not calibrated for this side of the thing. For 3 over 2. That's going to give me, now I'm not changing anything else. So that's still 1, still 12, that's still 6, that's still 6. I'm not changing anything with species 3, so aluminum's still 1. And I didn't change anything with carbon and oxygen. But what I'm changing is 11. So now if I multiply my fraction 3 over 2 times 2, I'm going to get 3 hydrogens. So 9 plus 3 is going to give me 12. So now I'm balanced, but I'm not done. So again, you can play around with changing the coefficient here, but then you're changing your oxygens and your carbons, and you have to go back to this species, and you're just going to find yourself in a loop. You're not going to find a way. So now I'm balanced, but I don't have my lowest whole number ratio because 3 over 2 isn't a whole number. But we did this earlier, we can do this again. Let's multiply the entire reaction by 2. That will get rid of that 2 in the denominator. But we can't just do H2, or we can't just do our final products. We have to multiply the entire equation by 2. So when we multiply our entire equation by 2, we will get 2Al solid plus 3 times 2 is 6. Aqueous, because it's dissolved in water, because it's an acid. That puts us 2 in front of species 3. Bless you. And at this point, you don't know how to predict that aluminum acetate is aqueous. You will later. We're going to talk about that in solutions. Plus, that gives us 3 in front of our H2 term. Our last step, just to be safe, you want to check this, make sure it is in fact balanced. Now we have only whole numbers, but we just want to make sure we didn't make a mistake. If we made a mistake, we will not have a final balanced equation. So this is 2, and our total hydrogens is going to be 24. Convince yourself of that. 12 carbons, 6 times 2 is 12. 6 times 2 oxygens is 12. On my other side, aluminum is 2. It's pretty straightforward. Carbon, we have 12. Oxygen, we have 12. And then hydrogen, first off, we have, remember, 3 times 3 is 9. Then that has to be multiplied by our coefficient. So that gives us 18 plus 6. 18 plus 6 is my 24. Wait, that's 3 times 6. Yep. So we are balanced. We are good. We have the lowest whole number ratio, and we're fully balanced. Aluminums are balanced, carbons are balanced, oxygens are balanced, and our hydrogens are balanced. So like I said, you don't have to do this, but for one that's this complicated, this chart can really help you keep everything. Basically, I'm just really following my numbers so I don't lose anything. I don't know if any high school teaches it like this. I just came up with this from teaching to make it clear, so I hope this has made it clear to you if you've ever had issues with balancing equations. Again, the more you practice, the better you get. It's a little bit of guess and check work sometimes. I hate guess and check. Like I said, for this one, it was easier to work with H2 because if we keep on changing this, then we have to change carbons. So always do what seems easier, and that'll really help you with these. So practice these, solve your puzzle. There we go. So for this one, B is correct because it's balanced. Again, if you are working with oxygen gas, you have to know that's O2. If you don't know it's O2, you won't be able to balance correctly. If you don't know how to take aluminum oxide and write the equation, you won't be able to balance correctly. All those are things we've talked about before in this chapter, so you still have to apply. So go ahead and make sure to convince yourself that B is balanced. A is the correct formulas for all of our molecules, but it's not balanced. The last thing, I'm going to go through this really quick because it's not really necessary that we cover it in too much detail right now. I've been talking about molecules, I've been talking about organic chemistry, so I just wanted to give you a short overview of the difference between organic compounds and inorganic compounds. Originally, any chemical that was able to be isolated from something living was considered organic. So it was thought for a long time that you couldn't make something in the lab that would be found in a living compound. Hence the term organic and where it came from. And then compounds coming from non-living environments were considered inorganic. Well, we know that that's not true. We can make things that are found in living compounds in the lab all the time. For example, urea. The body produces urea. We can make urea in the lab. I can make a sugar in the lab. The body produces sugar. The body is very, very specific on how it makes things, and it's very intricate, but we can make things in the lab that are chemically equivalent from what can be made by living things. So that's not a good definition. Also, organic compounds could decompose, and they thought at first that anything from a living thing could decompose, and that's not true. So now the actual definition of organic compounds is a compound that contains carbon is an organic compound. So anything that contains carbon is organic. Now typically carbon will be bonded with hydrogens, so we're usually considering organic chemistry as the study of carbons and hydrogens. But molecules that just have carbons and hydrogens don't react with very much besides combustion. So typically organic compounds have other amounts of elements that are nonpolar. Not nonpolar, that's not what I want to say. That are nonmetals, that's what I wanted to say. Oxygen, nitrogen, and phosphorus, sulfur being the most common, though sometimes we'll discuss boron and other nonmetals. And of course halogens. Halogens is another important one. But the main thing is carbon. So that's how we describe our organic compounds. Carbon atoms will typically form ionic bonds, and covalent bonds, we're usually bonding with nonmetals. Still have 5 minutes with you, so please don't start packing up just yet. If I don't cover it and your test is on it, they'll cry to me, so don't start packing up while I'm still lecturing. There's a certain amount of material I have to get through in this class for you to be successful in 106. So I gotta stick it in. Okay, so we have carbon likes to bond in 4 single bonds. It can also form 2 double bonds, 1 triple bond, but total carbon, when it's neutral, always forms 4 total bonds. You don't really have to memorize that right now. We will discuss why a bit later, and in organic chemistry, we will talk about why in a lot of detail. So most of you in here probably have to take organic, so you're going to be seeing this in more detail. But it's pretty unique because carbon can form long chains of bonds between other carbons, which is what's really unique about it, and why, even though we're really only talking about often about 7 or 8 elements, the amount of compounds are amazing. How many different compounds can form that do different things, that have different reactivity. I mean, you're required, most of you in here, to take 2 semesters of organic chemistry, organic 1 and organic 2. I have a PhD in organic chemistry, so I've studied and taken about 15 different organic chemistry classes. Again, this is only with 6 elements, 6 to 8 elements, and the way that they combine. So organic chemistry is very intricate, even though we're not. In fact, oftentimes organic chemists will only look at that little end of the periodic table. That's all we care about. I don't care what goes on the other side. I only care about those 6 elements. So it's amazing what can happen and how much we do. So the only thing I want you to know right now is when we talk about organic compounds and you hear the term hydrocarbon, and you probably have, especially because global warming is a discussion in a lot of things, and you hear hydrocarbon a lot, because hydrocarbons are found in oils, and we burn them for fuel. Hydrocarbons are simply compounds that contain only hydrogen and carbon, hence hydrocarbon. And again, we can have a bunch of different molecules. Now, once we have those other atoms, or double bonds or triple bonds, we call that functionalized hydrocarbons. And that functionality is what gives us reactivity. Most hydrocarbons, the only thing we can really do with it is burn them, and we do a lot of that. We burn a lot of hydrocarbons. But organic chemistry is the study of making compounds from organic-containing compounds, not burning them and forming CO2 and H2O. So we don't deal with too much combustion. Functional groups can be alcohols, thiols, carboxylic acids, amine. There's a lot more. You don't need to memorize them now. You're going to learn that a lot more later on. So that's where we're going to stop today. We're going to start with Chapter 4. Chapter 3 homework is due this weekend. Make sure you're doing it. Y'all have a good weekend. Y'all be surprised if you have a quiz sometime next week. Gotta keep you on your toes. And practice balancing those equations.